SoC demo video. It is our pleasure to demonstrate our chip to you. Our takeout project is sponsored by Apple and supervised by Professor Mingu. It is based on TSMC 65 nanometer tech node. The total area is 2.1 millimeter squared, and the maximum operating frequency is 252 megahertz.
Our chip is RISC-V based and integrates a custom vector processing unit, aka VPU, that excels at accelerating vector-heavy workloads, such as the vector multiplication and convolution. Let's see how it works. Okay, so this is the testing setup for our chip. Here is our PCB board, and our chip is located here. You can also see a clear version of the chip here in a different package. There are 4 switches on the board. The first one controls the power supply, and the second one enables the internal clock. The third is the reset for the test FSM that gates the clock. And the last one is the chip reset. Once I release the chip reset, the chip starts running. So the FPGA here is connected to the PC, and the MATLAB and the Vitus controls the FPGA to orchestrate the scan in, scan out, and data transfers. The PCB board here interfaces with the FPGA through a left shifter and the P mode connector. The FPGA drives the scan chain signal to scan instructions and data into the on-chip memory, and also to scan results back out. MATLAB then sends and receives the data frames to reconstruct the output, allowing us to visualize both the performance and the image processing effects. Today's demo shows a silicon-proof CPU-VPU heterogeneous chip that accelerates data parallel workloads under software control. The same workload is run in 2 modes, CPU only and CPU plus VPU. So first, let me show you a lightweight workload with relatively fewer vector operations. So first, let me turn on the power supply and turn on the FPGA. The light is also on. I need to set the enable into 1 and press enter. It starts to scan in the instruction and data. Now you can see the scan in is done, and then I will release the FSM reset and press enter again, and I will release the chip reset to let the chip work. Okay, I will start to scan out. Now the scan out is finished. That's the processed image in this algorithm. That's the executing time with the cycles count in CPU plus VPU mode. And then I switch to the only CPU mode and run the script.
A few moments later.
Okay, now you can see here is the processed image. That's the same with the CPU plus VPU mode. Through comparing 2 cycles, you can see the speed up here. The output is correct, but the speed up is limited because the workload is not dominated by data parallel kernels. After working through the full test flow and how we capture and present performance, you might be wondering how much speedup can this chip deliver when the workload is truly VPU dominant. Next, I will show a convolution-heavy workload to demonstrate the achievable acceleration. This demo runs a 3x3 filtering style kernel with a much higher fraction of repeated MAC operations. You can see here, the left one is with our VPU, and the right one is only use the CPU to process. Compare their cycles below and get the speed up. It's about 6 times, which is much higher. So this is where the VPU is utilized the most effectively. and the largest speedup is observed. Then I want to show up one more classic demo, which is about the severe edge detection. This demo compares the full-frame severe with the ROI severe that only processes a selected region. So you can see here, for the full-frame one, the speedup reaches about 3 times. And the ROI one is only 2 times. Since the ROI severe does less total vectorizable work, the VPU utilization ratio is lower than the full-frame severe, so the speedup is smaller.
So, here is the architecture of our low-power SoC. It's built around a RISC-V core, and the cool part is this vector processing unit. It takes the heavy lifting of processing vectorized data off our main CPU. Everything talks through an AXI bus, which makes the design very clean and fast. Think of it as a central highway. It connects the core to data memory, UART, and SPI. One key thing to notice is the scan chain on the left side. It gives us a backdoor to write directly to instruction memory and data memory, which helps us to debug the system much faster. Basically, it's a low-power RISC-V system, and it's optimized for vector processing.
After completing the RTL design and verification, we used Synopsys Design Compiler as our synthesize tool, and followed a bottom-up approach that matches the hierarchical structure of our chip, synthesizing from sub-modules up to the top and chip-level modules. The generated netlist files were then taken into Cadence Universe for automatic PNR. After integrating I/O pads, we obtained the final layout of our chip. At each stage of synthesize and physical design, we performed static timing analysis using prime time to ensure that all timing passes met our constraints. Before final tape-out, we also carry out comprehensive sign-off checks, including DRC, LVS, ESD, and so on, to validate that the chip would operate reliable under multiple process, voltage, and temperature corners. To support demonstration requirements for our chip, we also designed a dedicated PCB that provides voltage regulation, filtering, and decoupling circuits, and enables the connectivity with an FPGA for system-level testing.
Now, I will briefly introduce the control and debug parts of our chip, including the scan chain, a clock generator, and a finessing machine. It's one of the most important parts of our design that it allows us to test our chip after the chip is being fabricated. So in this diagram, you can see the scan chain is between the chip's I/O and the instruction memory and data memory. It is basically a 252-bit serial shift register that every bit connects to the instruction memory and also the data memory and some registers for clock generator. We control it through few pins, the scan in, scan out, and the two-phase clock consists of phi and phi bar, and also the scan I001, which is the scan enable, and also the load signal. So to write the chip state, we put the chain in scan in mode, shift in 252 bits on the scan in pin, and then set load signal to update the memories and control the registers. Then to read states, we just let the scan out cells sample memory data and then shift all the 252 bits out through the scan out pin. So with this one serial chain, we can both initialize the chip and also observe its internal behavior after execution. And then in this image shows our programmable clock generator. It is implemented by the ring oscillator here and also a divider controlled by the FC signal and DIV. We can also choose to use an external clock here by set the enable in signal. Then the clock signal is generated and sent to a small finessing machine that we designed. And the function is basically just gating this clock to decide whether the chip clock is off for the scan-in purpose or free running or enable for only a couple chosen number of cycles.
This slide summarizes our software and testing flow. First, we compile C test into IMEM and DMEM initialization. We write a C test program and compile it with the RISC-V GCC and linker script. The linker places instructions and data into the IMEM and DMEM address space, and the toolchain generates a header file that contains the initialization arrays for instruction and data memory. Second, we convert this initialization data into scan comments. MATLAB scripts read the IMEM and DMEM arrays from header file and serialize them into scan-in and scan-out sequences that match our scan chain interface. Third, we load the program via FPGA and verify the results. The FPGA, programmed with VTIS, acts as a scan controller. It shifts with IMEM and DMEM contents into the chip through the scan chain, starts the execution, and finally reads back scan-out data for validation. This way, we can use the same flow for RTL simulation and for post-silicon testing. Here is one example C test program that goes through our flow. It implements a simple swappable edge detection kernel on the 32 multi-32 image. All input data and output buffers and swappable filters are explicitly placed into the DMEM section, while the code stays in IMEM after linking. One important part is that the test calls our custom AIPE using inline assembly. We embedded our RISC-V vector instructions as dot word, so they can directly exercise the AIPE hardware. After compilation, this entire program becomes a sequence of hex values placed into the IMEM and DMEM arrays inside test.h. These hex values are what our scan chain flow loads into the chip for testing.
So we successfully designed, implemented, and taped out a fully functional system chip integrating a Pico RB32 RISC-V CPU core and a vector processing unit. Our chip delivers significant speed up on vector-heavy workloads and also demonstrate the potential of our design.
In the end, a huge thanks to Apple for their support. Your sponsorship and the resources were crucial in taking this project from RTL to actual silicon. We'd also like to thank our Professor Minggu So and our TAs Chuantang, Da Wang, and Mawson for their guidance and constructive feedback. Thank you again.